Hi friends, in today's lecture we shall be talking about the combinational circuits. A combinational circuit is one where the output at any time depends only on the present combination of inputs at that point of time with total disregard to the past state of the inputs. Several types of combinational logic circuits like adders, comparators, decoders, encoders, code converters, multiplexers and parity generators will be discussed in this and the following lectures. The logic gate is the most basic building block of combinational logic. The logic function performed by a combinational circuit is fully defined by a set of Boolean expressions. Figure here shows the block schematic representation of a generalized combinational circuit having n input variables and m output variables or simply outputs. Since the number of input variables is n, there are 2 to the power n possible combinations of bits at the input. Each output can be expressed in terms of input variables by a Boolean expression with the result that the generalized system of figure can be expressed by m Boolean expressions. As an illustration, Boolean expressions describing the function of 4 input or oblique NOR gate are given as y1 or output is equal to a plus b plus c plus d and y2 NOR output is equal to a plus b plus c plus d whole bar. Also, each of the input variables may be available as only the normal input on the input line designated for the purpose. In that case, the complemented input, if desired, can be generated by using an inverter as shown in figure, which illustrates the case of a 4 input 2 output combinational function. Also, each of the input variables may appear in 2 wires, one representing the normal literal and the other representing the complemented one as shown. Implementing combinational logic. The different steps involved in designing of combinational logic circuit are as follows. Statement of the problem, identification of input and output variables, expressing the relationship between the input and output variables, construction of a truth table to meet input output requirements, writing Boolean expressions for various output variables in terms of input variables, minimization of Boolean expressions, implementation of minimized Boolean expressions, and there are some guidelines which need to be followed while choosing the preferred form for hardware implementation. The implementation should have the minimum number of gates, with the gates used having the minimum number of inputs. There should be a minimum number of interconnections and the propagation time should be the shortest. Limiting on the driving capability of the gates should not be ignored. These are only the guidelines, not the rules. So, one should not generalize as to what constitutes an acceptable simplified Boolean expression. The importance of each of the above mentioned aspects is governed by the nature of the application. Arithmetic circuits, the basic building blocks. In this section, we will discuss those combinational logic building blocks that can be used to perform addition and subtraction operations on binary numbers. We will begin with the basic building blocks, namely half adder, full adder, half subtractor and full subtractor. Half adder. A half adder is an arithmetic circuit block that can be used to add 2 bits. Such a circuit thus has 2 inputs that represent the 2 bits to be added and 2 outputs, with one producing the sum output and the other producing the carry. Here we can see the truth table of half adder showing all possible input combinations and the corresponding outputs. The Boolean expression for the sum and carry outputs are given by the equations sum s is equal to a dot b bar plus a bar dot b. Carry c is given by a dot b. The first one, representing the sum output, is that of an XOR gate. The second one, representing the carry output, is that of an AND gate. However, these two expressions can certainly be represented in different forms using various laws and theorems of Boolean algebra to illustrate the flexibility that the designer has in hardware implementing as simple a combinational function as that of the half adder. We have learnt in earlier lectures on Boolean algebra how various logic gates can be implemented in the form of either only NAND gates or NOR gates. Although the simplest way to hardware implement a half adder would be to use a 2 input XOR gate for the sum output and a 2 input AND gate for the carry output as shown here. It could also be implemented by using an appropriate arrangement of either NAND or NOR gates. Figure here shows the implementation of a half adder with NAND gates only. A close look at the logic diagram reveals that one part of the circuit implements a 2 input XOR gate with 2 input NAND gates. The AND gate required to generate carry output is implemented by complementing an already available NAND output of the input variables. Full adder. A full adder circuit is an arithmetic circuit block that can be used to add 3 bits to produce a sum and a carry output. Such a building block becomes a necessity when it comes to adding binary numbers with a large number of bits. The full adder circuit overcomes the limitation of half adder, which can be used to add 2 bits only. Figure shows the truth table of a full adder circuit showing all possible input combinations and corresponding outputs. In order to arrive at the logic circuit for hardware implementation of a full adder, we will firstly write the Boolean expressions for the 2 output variables, that is the sum and carry outputs in terms of input variables. These expressions are then simplified by using any of the simplification techniques. The Boolean expressions for the 2 output variables are given in following equations for the sum output and for the carry output. For the sum output, S is equal to a bar dot b bar dot c in plus a bar dot b dot c in bar plus a dot b bar dot c in bar plus a dot b dot c in. and the carry output is given as A bar dot B dot Cn plus A dot B bar dot Cn plus A dot B dot Cn bar plus A dot B dot Cn. Now, we are to simplify the two expressions. We will do so with the help of Carnot mapping techniques. Carnot maps for the two expressions are given in figure A for the sum output and figure B for the carry output. As is clear from the two maps, the expression for the sum output cannot be simplified any further, whereas the simplified Boolean expression for C out is given by the equation where C out is equal to B dot C in plus A dot B plus A dot C in. Figure here shows the logic circuit diagram of the full adder. A full adder can also be seen to comprise of two half adders and an OR gate. The full adder of the type described forms the basic building block of binary adders. However, a single full adder circuit can be used to add 1-bit binary numbers only. A cascade arrangement of these adders can be used to construct adders capable of adding binary numbers with large number of bits. Half subtractor. We have seen in earlier lectures on digital arithmetic how subtraction of two given binary numbers can be carried out by adding 2's complement. This allows us to do a subtraction operation with adder circuits. A half subtractor is a combinational circuit that can be used to subtract one binary digit from another to produce a difference output and a borrow output. The borrow output here specifies whether a 1 has been borrowed to perform the subtraction. Figure here shows the truth table of a half subtractor. The Boolean expression for the two outputs are given by the following equations, where D is equal to A bar dot B plus A dot B bar and BO is equal to A bar dot B. It is obvious that there is no further scope for any simplification of the Boolean expressions given an XOR gate. The expression for the borrow output is that of an AND gate with input A complemented before it is fed to the gate. Figure shows the logic implementation of a half subtractor. Comparing a half subtractor with a half adder, we find that the expressions for the sum and difference outputs are just the same. The expression for borrow in the case of the half subtractor is also similar to what we have for carry in the case of the half adder. If the input A, that is the minuend, is complemented, an AND gate can be used to implement the borrow output. Full subtractor. A full subtractor performs subtraction operation on 2 bits, a minuend and a subtrahend, and also takes into consideration whether a 1 has already been borrowed by the previous adjacent lower minuend bit or not. As a result, there are 3 bits to be handled at the input of a full subtractor, namely the 2 bits to be subtracted and a borrow bit designed as bin. There are 2 outputs, namely the difference output D and borrow output BO. The borrow output bit tells whether the minuend bit needs to borrow a 1 from the next possible higher minuend bit. Figure shows the truth table of a full subtractor. The Boolean expressions for the two output variables are given by the following equations. D is equal to A bar dot B bar dot B in plus A bar dot B dot B in bar plus A dot B bar dot B in bar plus A dot B dot B in. Borrow output is equal to A bar dot B bar dot B in plus A bar dot B dot B in bar plus A bar dot B dot B in plus A dot B dot B in. The Carnot maps for the two expressions are given in figure for difference output D and borrow output BO. As is clear from the Carnot maps, no simplification is possible for the difference output D. The simplified expression for BO is given by the equation A bar dot B plus A bar B in plus B B in. Controlled inverter. A controlled inverter is needed when an adder is to be used as a subtractor. As explained earlier, subtraction is nothing but addition of the 2's complement of the subtrahend to the minuend. Thus, the first step towards practical implementation of a subtractor is to determine the 2's complement of the subtrahend, and for this one needs firstly to find 1's complement. A controlled inverter is used to find 1's complement. A 1-bit controlled inverter is nothing but a 2-input XOR gate with one of its inputs treated as a control input as shown in figure. When the control input is low, the input bit is passed as such to the output. When the control input is high, the input bit gets complemented at the output. The figure here shows an 8-bit controlled inverter of this type. When the control input is low, the output is the same as the input. When the control input is high, the output is 1's complement of the input. As an example, 11010010 at the input would produce 00101101 at the output when the control input is in a logic 1 state. Adder subtractor. Subtraction of two binary numbers can be accomplished by adding 2's complement of the subtrahend to the minuend and disregarding the final carry, if any. If the MSB bit in the result of addition is 0, then the result of addition is the correct answer. If the MSB bit is a 1, this implies that the answer has a negative sign. The true magnitude in this case is given by 2's complement of the result of addition. Full adders can be used to perform subtraction provided we have the necessary additional hardware to generate 2's complement of the subtrahend and disregard the final carry or overflow. Figure shows one such hardware arrangement. A close look at the diagram would reveal that it is the hardware arrangement for a 4-bit binary adder, with the exception that the bits of one of the binary numbers are fed through controlled inverters. The control input here is referred to as the sub input. When the sub input is in logic 0 state, the 4 bits of the binary number B3, B2, B1, B0 are passed on as such to the B inputs of the corresponding full adders. The output of the full adders in this case gives the result of addition of two numbers. When the sub input is in logic 1 state, 4 bits of one of the numbers B3, B2, B1, B0 in the present case get complemented. If the same one is also fed to the carry in of the LSB full adder, what we finally achieve is the addition of 2's complement and not 1's complement. Thus, in the adder arrangement as shown in figure, we are basically adding 2's complement of B3, B2, B1, B0 to A3, A2, A1, A0. The output of the full adder in this case gives the result of subtraction of the two numbers. The arrangement shown achieves A minus B, the final carry, that is, the carry out of the MSB full adder is ignored if it is not displayed. So, friends, here we come to the end of our discussion in this lecture, and therefore, we sum up. A combinational circuit is one where the output at any time depends only on the present combination of inputs at that point of time with total disregard to the past state of the inputs. In this lecture, we learnt the basic logic behind the combinational circuit, the basic building block of combinational logic like half adders, full adders and subtractors. So, that is it for today. See you in the next lecture. Thank you very much.